Friends, we'll start with X-ray diffraction now. So far we have talked about how X-rays are generated and what are characteristic X-rays, what are white radiation, and we also talked about how to cut off certain radiation, characteristic radiation, from a mixture of characteristic radiations. For example, what is called filtering, we talked about it. So now we have an X-ray of a particular radiation, let's say called copper K alpha, let's say. So if I use this copper K alpha onto a sample and I want to use it to identify the crystal structure of that sample, how does the whole thing work? To understand this, let us understand the whole concept of the diffraction. So the diffraction works from a principle that materials are crystalline in nature. In the first class, we talked about crystalline amorphous materials, and crystalline materials are those which have periodicity, we said, either periodicity or quasi-periodicity. We also introduced the concept of quasi-crystals. So if I assume that crystals have certain periodic arrangement of atoms, and we can always say that there are certain atomic planes in them. Okay? And we also talked in one of the classes how to index these planes, and we started calling them with certain numbers called HKL. And let's say if I take a crystal with certain atomic planes, a number of planes in them which are all parallel to each other, and the distance between these planes is what is called D, which is called interplanar distance. And if an X-ray now is falling on this particular sample with some incident X-ray with certain theta angle of incidence, it is now diffracted like this, and we all know that the diffracted beam also will have the same angle, okay, because this is basically elastic collision. So if it is like that with a certain same angle as theta, now if I look at a set of parallel X-ray beams with another beam which is parallel to this falling on this and then again getting diffracted like this, now this beam that is coming out, the diffracted beams that are coming out, whether they have an intensity or not depends on whether there is a constructive interference between these beams coming from parallel planes. Okay, this is an incident beam, this is a diffracted beam. If there is a constructive interference between these, then only you will have some intensity of a diffracted beam. If there is no constructive interference, you will not. And this constructive interference has been given by a certain condition that if I look at the path traveled by these X-rays, for example, if I draw a perpendicular from here and draw another perpendicular from here, you can see that this, if I call this as 1, if I call this as 2, and if I call it as 1 dash and call this as 2 dash, 1 is an incident beam falling on certain plane, top plane. 2 is another incident beam falling on plane number 2, let's say some other plane which is parallel to it. And again 1 dash is a diffracted beam coming from the one incident beam 1. 2 dash is a diffracted beam coming from this. If I look at it, this 1 and 2 up to here, they have the same length, right? And similarly 1 dash and 2 dash up to here, they have the same length. Only difference is the 2 is traveling an extra path by this. Okay, so this is what is called the path difference for 2 with respect to 1. And if this path difference is integral multiples of lambda, then only the constructive interference will take place. This is the principle of diffraction. If you want constructive interference so that the beam has certain intensity, you have to have this condition satisfied. What is the path difference? To understand this, we know that if this is theta, this is 90 minus theta. right? Because this is a right angle. Okay, so if this is 90 minus theta, if I draw a line here, okay, and this is 90 degrees, so this is also theta, right? So similarly, this is also theta. If that is the case, then I can write sine theta is this. If I call this as x distance, okay, x divided by this, right, which is nothing but d. So now this is also another x, right? So you can always say, so x is d sine theta, and now because this whole distance is 2x, 2x is 2d sine theta. This is x, this is also x. So the path difference is for us is 2x, right? This is the path difference, this one plus this one, and that is 2d sine theta. So the condition is n lambda is 2d sine theta. This is what people call it as Bragg's law, the condition for the diffraction to take place. What do I mean by diffraction? Condition for the diffracted beam to have some intensity. Otherwise diffraction might be taking place, but the diffracted beam does not have any intensity. If this condition is not satisfied, the diffracted beam will not have any intensity. You will not see the diffracted beam. So if you want to see the diffracted beam, this condition has to be satisfied. And this is what is the whole of X-ray diffraction. And incidentally, this is true for even the electron diffraction. Any beam that is falling, whether it is X-ray beam falling or an electron beam falling, this condition has to be satisfied. So this is the condition for diffraction. We will come to electron diffraction a little later. There we will see how things get modified a little bit. So this is something let us remember, and we will see that this will cause certain diffraction to happen, and this diffraction is what is used for identifying the crystal structures. And in this, what is D? D is called interplanar distance. Distance between certain planes, and this interplanar distance is related to the plane, the nomenclature that we are using for the plane. That means the indices of the plane. For a cube, usually people have seen that this is given by this formula. For different crystal systems, it is different. Let's only use the cubic. It is very simple. So D is related to lattice parameter, and it is also related to the HKL. So D for a given HKL is this. And you can see that because D is inversely proportional to the HKL, so as the planes, the indices increase. For example, for a 100 plane, D of 100 is what? Is A by square root of 1 square plus 0 square plus 0 square, and as a result it is A by 1. This is equal to A. If I take a 200 plane, D of 200 is what? Is 2 square here, and 0 square and 0 square. So 2 square is 4, square root of 4 is 2, so A by 2. So you can see that as the indices are increasing, that means I go from low index planes to high index planes. For example, if I take 222, D of 222 is A by square root 12. 4 plus 4 plus 4, right? So you can see that as I increase the indices, D is decreasing. D is inversely proportional to 1 by this, A square plus K square plus L square. the root. This is something which we have to remember. As we go along, we will be using this more and more. So I know that this particular D in this formula is related to the lattice parameter and the plane that we are talking about. For a given plane, there is a particular D. Because A is fixed, the plane is fixed, then D is fixed. If the D is fixed, theta is fixed. If lambda is fixed. So we are going to see how various X-ray diffraction techniques have come out based on this simple formula called n lambda equal to 2d sin theta. And out of these techniques, the most historically, the first technique that has been developed is called Lave technique. In a Lave technique, what people have done is they have taken a white radiation, that means X-rays with various varied lambda. X-ray with a bunch of lambdas. You remember we have talked about this radiation where intensity versus lambda. So you can have a radiation where X-rays have varied lambdas and varied intensities. And such a lambda if I take and send it to a sample with which is a single crystal. Okay. A single crystal is what? Single crystal is that where the atoms are periodically arranged inside the crystal in a particular orientation. So it has one fixed orientation, and this whole single crystal can be called as one single grain. And if I send an X-ray beam with lambda which is variable lambda, but this is a single crystal, then the diffracted beam that is coming out, this is a transmitted beam, and the diffracted beams that come out will come out like this. And there are different atomic planes inside the single crystal. If this is aluminum single crystal, you will have different planes, 100, 200 and all those. For each plane chooses one of the lambda so that it satisfies this condition. Because for a given plane, the D is fixed. Okay? If the D is fixed, the lambda that can give a particular diffraction is also fixed. So every D, every HKL will choose, every HKL will have certain D, and this D chooses a particular lambda so that it gives you a particular theta. So this theta that you are seeing, in fact, to be very frank with you, this is actually not theta. To explain this better, if you remember, if I have the X-ray beam falling like this and the diffracted beam coming like this, this is the incident beam, this is a diffracted beam. If this is theta and if this is theta, then what is the transmitted beam? Transmitted beam goes like this. Okay, so this is a transmitted beam, this is a diffracted beam. So the angle, this angle is also theta, right? Because from the geometry of parallel construction, we can say whenever there is a line, okay, which is being intersected by an angular line, if this angle is theta, this angle is also theta. If this is theta and this is also theta, we know. So the angle between transmitted beam and diffracted beam is always 2 theta. The angle between transmitted beam and diffracted beam is 2 theta. That means if this is my incident beam and this is the transmitted beam, and if this is the diffracted beam D, this is 2 theta. You have to always remember this. That is the reason why in our X-ray diffraction we always use the word 2 theta more rather than actually theta. Because the transmitted beam, if the beam is falling like this and my transmitted beam is parallel to the beam which is falling, and all the diffracted beams I am measuring with respect to the transmitted beam. And because I am measuring with respect to the transmitted beam, and this angle is 2 theta as you can see from this construction, so this is 2 theta. And so each particular HKL plane will choose a particular lambda so that it gives you diffraction at a particular theta, that means at a particular 2 theta. So this particular diffracted beam that is coming out will have certain indices HKL. And this that is coming out will not be like a single beam, but it will come out as a cone of beams going through. How does this cone come? Because if I choose a 1, 0, 0 plane and choose a 0, 1, 0 plane and 0, 0, 1 plane, for example, all three of them will have the same D, right? How do I see that? Because you can see this is the relation. If this is the relation, D of 1, 0, 0 is A by 1 square plus 0 square plus 0 square. That is equal to A by 1. That is A. So if I am talking about 0, 1, 0, it is again 0 square plus 1 plus 0. Again it is A. Even if I am choosing this, also it is the same. Even if I choose 2, 0, 0 and 0, 2, 0 and 0, 0, 2, it is also the same case. This will be A by 2. D of 2, 0, 0 will be equal to A by 2. D of 0, 2, 0 will also be A by 2. D of 0, 0, 2 will also be equal to A by 2. All of them are the same. If all of them are the same, okay, if the D gets fixed, then theta gets fixed because it chooses a particular lambda to give a theta. So that means the angle of diffracted beam for this plane and this plane and this plane is same. That means this angle is same. But then what will be the difference? The orientation is different. So if diffracted beams come like a cone and one beam will be going like this, one beam will be going like this, another beam will be going like this. Each of them, one may be 1, 0, 0, one may be 0, 0, 1, one may be 0, 1, 0. But all of them will have the same angle. The solid angle will be the same. So that is how this whole thing comes out like a cone. This cone of X-rays with same family, all of them. So one family of planes will have all their beams going on the surface of this cone. Okay? And they will all have the same angle. Now if I choose some other plane, H2K2L2, let us say, H2K2L2, which is different from this family, will have a different angle, different 2 theta. Because the D will be different, so as a result theta will be different. So as a result, if I put a screen here, all these diffracted beams will come and hit this particular photosensitive screen, and on the photosensitive screen, when a beam hits a screen, it forms like a dot. You will see like a dot. Like any laser beam falls onto this, you see a dot. It is a beam that is coming, but you see only as a dot. Right? So when this diffracted beam comes here, it forms a dot, and by looking at the arrangement of these dots, with respect to the transmitted beam also falls here, forms a dot. So by looking at the arrangement of, and if I can measure these distances will give me an idea of this theta, and from the theta I can go back and calculate what would be the D. And this is how people can use, put a single crystal, use a variable lambda and find out each beam corresponds to what particular plane. And from that can find out by looking at the arrangement of this, they can find out what crystal structure. When we are going to come to electron diffraction, I will explain this a little more detail, because electron diffraction exactly uses this kind of a Lave method. We will hold on for a while. This is one of the methods. The second method that is used is what is called, of course in this people also use what is called back diffraction, back scattered. For example, if you have a sample here, okay, if the beam that is, if the HKL of the sample which is getting diffracted is such that the theta is greater than, if this is the 2 theta, if this 2 theta is equal to 90 degrees, then the beam will go like this, right, the diffracted beam. If the 2 theta is greater than 90 degrees, what would happen? The beam, diffracted beam will go like this, right? So if the 2 theta is less than 90 degrees, the beams will all fall onto a screen like this, and this is what is called transmission mode. If the 2 theta, how does this 2 theta come? This 2 theta is related to D, and the D is related to HKL, right? So depending on what HKL I am seeing, and can I not see here the D and theta, because D I can write it as n lambda by 2 sin theta, or I will do the reverse, the sin theta is equal to n lambda by 2d. Right? That means what? If the d is decreasing, then the theta will increase. D is decreasing. When does the d decrease? If the d is decreasing, then HKL is increasing. Or the other words, if HKL is increasing, then the d will decrease. If the d decreases, then the theta will increase. Why? You can see here. If I have chosen 100, then the d was, for d of 100 was A. D of 200 was A by 2. D of 220 was A by root 8. You can see that as the HKL is increasing, the D is decreasing. A by 2 is smaller than A by root 8 is smaller than A by 2. So you can see that as the HKL is increasing, as I am going from low index planes to high index planes, the D is decreasing. If the D is decreasing, because sin theta is inversely proportional to D, the theta will increase. So it is possible that some low index planes will have thetas lower. You can see if the HKL is low, the theta is low. If the HKL is large, then the theta is large. So low index planes, for example, 100 plane will have smaller theta, 220 plane will have larger theta. So it is possible that there are some HKL planes where their theta is such that the 2 theta is greater than 90. If it is greater than 90, then the beam will come like this. So all those beams will come like this. Then you have to have one more screen here. Okay, such that the beam which is with a hole here, so that the transmitted X-ray beam will go through this hole of that particular screen, and then it gets the beams, the diffracted beam come in a reflected mode and come and hit this. This is what is called backscattered diffraction. This is called transmitted mode. This is called backscattered mode. So if I have two screens, photosensitive screens, and I look at both of them, some of the planes I will be able to catch here, some of the planes I will be able to catch here, and looking at all, wherever these planes are hitting, looking at these distances, I will be able to calculate the D spacings, and from the D spacings I can calculate the A, and I will be able to find it out. We will come to how to calculate it a little later, and I am just only giving you a principle behind the technique, and the actual calculation we will come to it after a little while. So you can see that there are two modes in the Lavey method. One is called transmitted mode, which is used for low index planes where the 2 theta is less than, the 2 theta is less than 90 degrees. Wherever the 2 theta is greater than 90 degrees, that means for high index planes where the 2 theta goes beyond 90 degrees, you use a backscattered. And that is how you can find out the crystal structure. And now if you go to the next method, these are all more of historical in nature. Nobody other than I would say physicists who are dealing with single crystals. There are very few people who deal with actually single crystals. Most of the material scientists deal with polycrystalline materials with so many grains inside and sometimes even so many phases in it. We rarely even deal with single phase materials. So as a result, the situation is more complicated. So as a result, most of the people do not use Lavey method anymore. The second technique is what is called rotating crystal. Again, I will also give you just because of historical importance. Otherwise, it is not a very popular technique for polycrystalline material. Here again, we use a fixed lambda and take a single crystal and keep rotating the single crystal. Okay, it is rotated like this, and an X-ray beam falls on it. And because this is being rotated, all the X-ray beams that are the diffracted beams that are coming out will come and fall onto a cylindrical screen. A cylindrical sheet is kept. If you put a cylindrical sheet which is a photosensitive sheet with some hole here and with some other hole here, so that the transmitted beam can go, and you will see that this particular diffracted beams fall on this screen, and because this is rotating, okay, it is a cone of X-rays which are falling. So what you see is, if you open up this sheet, finally the cylinder, if it is opened up, you see that this is where it has fallen, and the X-ray diffracted beams will fall as spots on a single line. You can see this cone, there are so many X-rays of a same what is called family, all going like a cone and falling on to this cylindrical screen, and if I open up the screen, you will see they will all look like spots on one single line. So you will see different lines like this, and if by measuring this distance, I will be able to know what is the angle, because this distance is related to this angle. If this is my 2 theta, so from the center to whatever particular lines are, for each line I can measure the distance, and this distance gives me an idea of angle, and from the angle I can back calculate, find out the D, and from the D I can find out what is the lattice parameter. So this is how we can be able to find out for again single crystals. Both Lave technique and rotating crystal techniques are used for single crystal to find out what is the orientation of the single crystal, particularly because for many physical property measurements, such as techniques where you have let's say silicon single crystals and things like that, which are used for physical properties like a semiconducting applications, you need to have the crystal with a particular orientation. I want to know which orientation is that, and that can be found out from this. But the most popular technique is what is called powder diffraction. Powder diffraction also has a historical evolution, I should say, where people used to use a camera in the beginning. This is what people call it as Debye-Scherrer camera, where what people do is they take a sample which is a powder sample, where they send a beam onto the sample. Because this is a powder sample, it has so many grains, so this is a polycrystalline sample. So what we are doing here is we are using a fixed lambda. Please remember, in the Lave technique we are using a variable lambda. In the rotating crystal we are using a fixed lambda. Again, in the powder diffraction we are using a fixed lambda. What do I mean by fixed lambda? I have taken an X-ray which has the K alpha, K beta. I have done the filtering, removed the K beta, and I am using only the K alpha monochromatic. So I made sure that one single lambda is falling onto my sample. Okay, and now if it is falling onto my sample, now what I see is again a diffraction that is happening, and this diffraction is happening like this. And this is the transmitted beam, and this is 2 theta. And what I do is I again, in order to make sure that this diffracted beams are collected, I put a film like this, okay, with a kind of it's like a strip of film, which is so you have a beam coming like this, and the beam falls onto a sample, and the beam comes out in all the directions, and you put a strip of film which is like a cylindrical strip of film, and the beam falls here. And when you open up the strip is looking like this, with this is the transmitted beam, and the diffracted beams look like this, like arcs, because this falls and a number of radiations fall and it looks like an arc. And now this distance, if I measure, this distance is called S. And this distance, if I can correlate, I can say if this distance, if this is the called R, which is the radius of that particular circle, then I can say if this is 2 theta, 2 theta is this, is if I call this as S, okay, sine 2 theta, sine of this is S by R. Okay. And so you can say if for small angles, I can assume sine theta is equal to sine theta. So people usually write it as R2 theta is equal to S. This is only valid for smaller angles. Whenever angles are smaller, sine theta can be approximated to theta. All of us know this. Okay. So simply people use this kind of a formula, R2 theta equal to S. And if I know the R, and if I measure what is this distance after the diffraction experiment has been conducted, I just simply measure this distance, and from the distance I can find out the theta. If I know what is the R for my cylindrical film that is being used. So once I know the R for the whole camera, camera is like a cylindrical camera, and I can find out the S. S can be measured, R is already known, so 2 theta can be measured, and once I know the 2 theta, I can use again the formula to this formula to find out what is the D, because already lambda I know what lambda, so I know the theta, and from the theta I can find out the D, and once I find out the D, I can do this. It is not so simple. I will come to it how to do this, because here D is connected to both A and HKL. How do I find out both A and HKL from one single D? Is going to be difficult. We will try to see how to solve that problem as we go along. So this is all about various methods that are used, and the next method that has come out, which has become the most popular, is no more this camera method. Nobody nowadays uses any camera. They use what is called diffractometer. People call it as powder diffractometer. Most of the people who buy XRD equipment, they are only buying this diffractometer, where you have a sample onto which X-rays fall, and the diffracted beams are coming out, and you have a detector which keeps on rotating, okay, in a particular arc fashion, and keeps on collecting all the X-rays which are falling on various angles. And this is like a counter. It keeps on counting the energy of this beam that is coming. And so you will see that when depending on what are the planes which are giving diffraction, when this keeps on moving, only at a certain angles it suddenly receives a peak, receives a beam that is coming out, diffracted beam. It may not get any beam when it is here, but it may get a beam when it is here. But it may not get any beam when it is here, but it may get a beam when it is here, depending on which are the planes which are diffracting. So you will see, if I put collect all this and plot the intensity versus 2 theta, you will see suddenly there are certain peaks here. At certain fixed angles. You will know very soon why they are at fixed angles, and why not there are so many peaks at all the angles, but only certain fixed angles you start seeing. We will see as we go along. So what we do is, as it keeps on rotating, which is called a goniometer, and as it keeps on rotating, it collects all these and then puts it, and while doing this, you will be able to see that there are different peaks with different intensities, and I need to understand what are these peaks from the angle, and I also need to understand what is the structure corresponding to this material. So from this kind of a diffraction pattern, what I get only is 2 theta. From the 2 theta, can I find out the structure and also find out the lattice parameter? Whenever I say determining the nature, crystal structure of a sample, what I mean is 2. One, I need to know what is the crystal structure. Second, I need to know what are the lattice parameters. Only when I know both these, I can say I have determined the crystal structure. Otherwise not. Simply knowing that this is FCC, you see there are so many FCCs. For example, aluminum is FCC. Okay, and I also know that the platinum is FCC, nickel is FCC. So all of them are FCC. So which material it is? How do I know? Only by knowing the lattice parameter. The lattice parameter of aluminum is different, the lattice parameter of platinum is different, lattice parameter of nickel is different. So only when I know that it is FCC and it has this lattice parameter, then only I can assign, oh, this is aluminum. Okay? Until then, I will not be able to say what material it is. So my goal is to see that I know the structure, I know the lattice parameters. So now the question is how to find out this. So can I use a diffractometer to do this? We say yes. How do we do it is what we are going to see right now. To understand this, I need to know one more aspect which we have not introduced so far. That is, in a diffraction pattern which has an intensity versus 2 theta, I get a peak like this, let's say. This peak has two characteristics. One, it has a position, it has a certain intensity. Of course, it also has certain breadth. In principle, every X-ray diffracted beam should be only a single vertical line. In principle, if perfect constructive interference and perfect destructive interference takes place, you should actually get this. The reason is lambda equal to 2d sin theta. What does it say? That means constructive interference takes place only when the diffraction angle is a Bragg angle. At any angle smaller than theta b or larger than theta b, the intensity has to be 0. I equal to 0. That is the condition of Bragg's condition. At theta equal to theta b, there is certain intensity. I is non-zero. What is the actual value? We will see it a little later, but it is a non-zero. But the moment theta is either smaller than theta b or larger than, it should be actually go to 0. But you see it does not. And you see that the XRD peaks usually will have, rather than a line like this, it will have a profile like this with certain breadth at various positions. And this is what we call it as peak broadening. And this peak broadening is characterized by what is called FWHM. Because the broadening is varying from bottom to top. In order to give a particular characteristic broadening, we take the full height and take half of it and find out what is the width at half the intensity, h by 2. Full width at half maximum. That is the acronym for this. Full width at half maximum. Measure the full width at half the maximum height is what is a representative of this. Why does this happen? It happens because of a number of reasons. We will see to it a little later and discuss how I can use this to find out variety of stuff. So we will also see, because this is related to what is called strain inside the material. This is also related to the grain size of the material. So we can find out variety of things by doing this. It is also related to what is called instrumental broadening. Instrument itself gives some broadening, and we will see as we go along. So if I look at the XRD pattern, as I said, it has a position, it has an intensity. Of course, it also has a breadth. These are the three characteristics. So position, intensity, and breadth. These are the three characteristics of anything. When I say intensity, people usually have a tendency just to measure the height. In principle, that is wrong. What you have to do is find out the area under the peak. This is what we call it as the integrated intensity. I will tell you a little later why this becomes important. When we are going to deal with how this peak broadening matters, at that time I will tell you why integrated intensity is important. Sometimes you may see that the peak may be broad. Sometimes you may see a peak may be very sharp. The same material, you would see this happening. For example, if I take aluminum, let us say, by some means I make it nano. Okay, I do regularly in my research, we do what is called high energy ball milling. So if you take aluminum and do this ball milling, what you see is when you have not done the ball milling, aluminum may give you a certain peak like this. The moment I have done ball milling, the peak becomes like this. The peak position will not change, but peak becomes broad. The area under this peak and the area under this peak will always be the same. So for a given HKL, the I is fixed. What does that I depend on is what we are going to see right now. Okay, so we say that the peak position depends only on the lattice parameter. We will come to it as we see it, because you can see that D is A by square root H square plus K square plus L square. So that means what? And we know the lambda equal to 2D sin theta. This is what we call it as first order reflection. N is taken as 1. So first order reflection, lambda equal to 2D sin theta. So that means theta depends on D for a given lambda. Because in powder diffraction we are fixing the lambda. Lambda is always fixed. So I am using a monochromatic radiation. If I am using monochromatic radiation and theta depends only on D. D depends on A. Right? So as a result, we always say the peak position depends on the size of the lattice. Because A tells you how big is the lattice or how small is the lattice. So if the lattice is very big, if the A is large, then the D is large. If the D is large, the theta is small. Why? You can see sin theta is inversely proportional to D. So as a result, we can say the position, peak position depends only on A. For a cubic, if it is non-cubic, it depends on A, B, C, all those things. But we can say that the peak position depends on lattice size, whereas peak intensity depends on something else. What does it depend on is what we will see right now. So please remember, every XRD peak has three characteristics. It has a position, it has an intensity, and it has a breadth. We will try to attack all of them to find out what do they give information to us. So let's look at this peak intensity. Peak intensity, people have found out, is related to what is called square of a structure factor. What is structure factor? Structure factor is, if I take a sample and if I send my X-rays, the X-rays are getting diffracted. This is the transmitted beam, this is the diffracted beam, this is 2 theta. They are getting diffracted. Where are they getting diffracted? What is diffracting them? It is the electrons inside the material which are diffracting it. Right? This material has certain electrons. The X-rays are interacting with those electrons, and these electrons are the ones which are getting causing the diffraction to happen. So as a result, this diffraction is coming from the unit cell. So if I know how many electrons are there inside a unit cell, okay, I will be able to know what is the intensity of the diffracted beam that is coming out. So this particular diffracted beam, this is coming out, is related to the diffraction that is happening from the whole unit cell, because unit cell is the building block for us. If I am talking of aluminum, aluminum has certain unit cell. Okay, if it is iron, iron has certain unit cell. So it is the diffraction that is taking place from one single unit cell is what is called F. Okay, if we will stop now and then continue in the next class.